Welcome to chapter 26. In our last chapter, we looked at the Milky Way galaxy, which probably looks very similar to this from the outside, but we can't see it from the outside because it's too far away to be able to take an image and then send it back to us. So we look through other galaxies and make comparisons. And we believe that our nearest large spiral neighbor, this one, the Andromeda galaxy M31, is very similar in its appearance to us. One of the things we'll look at in this chapter is the sort of cataloging and assortment of galaxies that are out there. So without any further ado, let me see if I can share my screen with you. I can get rid of that. We don't need to do that here. And let's start the slideshow. Galaxies, there we are. So as we talked about before, the idea of a galaxy is relatively new in the history of science. And from William Herschel on forward, the idea of our own galaxy grew and grew and grew until about 100 years ago, almost exactly 100 years ago. There was what was called the Great Debate in 1920. And they were debating whether or not the whole universe was the Milky Way, just one big galaxy, or whether there were other galaxies that were out there. And we had two people, Shapley here and Curtis, who argued on different sides of the argument. And the truth is, by the end of the argument, both of them were right in different ways. Shapley here thought that we were one big, enormous galactic system. Well, that's wrong, but many of the details that he put into his argument ended up being correct for each individual galaxy. And Curtis had the idea that these other spirals that we were seeing, like the Andromeda here, with older telescopes, sort of looked like just another nebula or a complex nebula, but still within our own system of stars in the galaxy. He argued that they were distant and separate. Interestingly enough, a lot of the details he put into this theory were wrong. So they were both right in a lot of different ways, and it sort of went to show how science develops over time. The great debate on galaxies is in fact a good final project topic if you're still looking for one at this point along the way. But this debate is only 100 years old. And one of the things I was hoping to do that got derailed because of the different things that are going on keeping us all at home right now was to have a great debate reenacted on our campus. And I may still try to do something like that virtually if I can find enough participants to do it. So I'll keep you informed if that comes about. Of course, a few years after this great debate, we have a guy named Hubble, you've undoubtedly heard of him, who came along and started analyzing these spiral nebulae and other kinds of things that were in the sky that may or may not have been farther away than we originally thought. And he used some of the major equipment that we had that were put together by telescope makers such as Hale, and we talked a little bit about Hale when we talked about different kinds of telescopes, especially in Astronomy 101. And one of the things that we see that's important in this is that we're finally reaching the technological point by the 1920s and 30s and 40s to actually get enough light from these distant objects to make assessments of them and to figure out what the structures were. And one of the things that he did was he looked for variable stars. Remember when we were talking about different kinds of stars? There were some stars that would sort of brighten and dim and brighten and dim. And we saw that the brightening and the dimming of those stars occurs according to a pattern. And you know what kind of star it is exactly by the pattern that it gives. If it brightens in 50 days, if it brightens in 60 days, we know what it is. Well, if we can find those same stars way over there in Andromeda, and we find those stars closer to us, we can actually measure the distance based on how bright they are of that one way over there and the one that's here. If we have two light bulbs and we know that they're both 100-watt light bulbs, and we have one right here in front of our face and one way over here, Well, we can measure how far away the one way over here is because we know it's a 100-watt bulb. And so we can measure how much the light is diminishing when it gets to us. Cepheid variables are stars very much like that. We call them standard candles. Don't ask me why. Actually, you can ask me why. It's a long story. And in fact, how we use that kind of terminology might also make a good final project. But using these Cepheid variables, he found that they were brightening and dimming and brightening and dimming and brightening and dimming out in Andromeda. But they were much, much, much fainter than any of the ones that we saw in our own galaxy. So he knew that they were a long, long, long way away. And that is really what made the universe into a collection of galaxies. It was that discovery from Hubble. And so when we look at the galaxies, we see there's quite a zoo out there. So we actually use the terminology zoology. And what we'll look for are the different kinds of galaxies that are out there and how we put them together into a tree. It's not a tree of life the way we have in biology, but we have an elementary tree called the tuning fork, and that comes from Hubble as well. This is a basic classification system, and there are 4 main types. There are spirals. Of course, we've got an example here. We've got barred spirals. I've talked about that before. We live in one. We've got a little bit of a bar that the arms come off of. We have ellipticals, which are sort of goose egg galaxies. And if you look closely at the bulge of a lot of spiral galaxies, they look like elliptical galaxies. And then we have irregular galaxies, and I sometimes call those splatter galaxies as well, because they can go every which way, and often those are the result of collisions between different galaxies. So let's start by looking at spiral galaxies. We can see here two views of a spiral galaxy called the fireworks galaxy. And it's called the fireworks galaxy because we see lots of blue. We see lots of star formation taking place largely in the arms as the arms spiral around. This is a smaller galaxy. It was discovered by our guy, William Herschel. Again, there's that name, before the 1800s. Now, he did not know this was a galaxy. That's something to keep in mind. It's 18 million light years away. The Andromeda behind me here is a little over 2 million light years away. But Herschel had no idea how far away it was, and he thought it was another nebula within our own galaxy. But as we look at it through the different kinds of images that we have here, we can see this is a sort of a modified X-ray over here, and this is a sort of a visual light plus a little bit of an enhancement, which probably includes infrared. We can see that there's a lot of gas and dust, and we can see a lot of star formation, particularly in the arms here. See, it's a sort of yellowish, reddish color in the center here, but we've got a bluish, more energy is happening in that area there. Here's another image of the Andromeda galaxy. We can see a lot of gas and dust that is part of the intergalactic stellar formation that's there. The number of the distance sort of yo-yos up and down. 2 to 2.5 million light years is a good number to sort of stick in your mind there along the way. We see it has satellite galaxies. It has 2 different galaxies that are orbiting it in close range, just like our small and large Magellanic Clouds are orbiting us in close range. There are other galaxies that are also in a wider arc going around the Andromeda galaxy, just as there are a couple that are going around us at a wider thing too. And we're really, the 2 of us, the Milky Way galaxy that we're in and the Andromeda galaxy here, are the 2 big actors in our local group. And our 2 galaxies are pulling towards each other along the way. Here we can see M100. Remember, the M numbers are the Messier numbers, the guy who put together the catalog to keep people from rediscovering the same things over and over again. So anytime something has an M number, we know that it's been known for quite a while. May not have been known for what it was, but we knew there was an object there. When we see NGC, the new general catalog, that again goes back to our guy Herschel, who is expanding the catalog. And here we see a spiral galaxy on edge. So we're seeing it as if it were sort of a record or a CD, if we're sort of looking at it this way, or we're looking at it edge on. We're looking at the edge here of NGC 4565. And one of the things we can see is we have the dust trail there, just like we have the dust trail in the Andromeda galaxy there. So we have gas and dust that is forming into stars and planets and planetary systems that are there. So here we have a bulge. Here we have the disk, which includes the spiral arms. Here we have gas and dust, and we can see some dust trails that are in there as well. So we have a disk that's flattened. We have everything going around a supermassive black hole somewhere in the center here. I don't know of too many spiral galaxies that have been confirmed to not have one. We have some that we haven't discovered it yet, but well, we pretty much suspect that everyone has something like that. Some have very well-defined arms, and our galaxy, even though we can't see it from the outside, has pretty well-defined arms. So does the Andromeda galaxy as well. Some of them do not have arms that are as well-defined along the way. And those are called flocculent galaxies. This is a flocculent galaxy here. As you see, we can barely make out the arms, and we can tell that there's a spiral structure in there, but it hasn't gotten its act together. So this might be like a pinwheel with a bunch of feathers or a bunch of streamers on it as it's sort of going around in there. And there's a lot of gas and dust, a lot of things that are going to be collapsing into stars, but perhaps not yet, because we don't see a lot of blue when we're looking at this. And blue colors would indicate stellar formation. And then here we have a barred spiral, and this has a very pronounced bar. This has a really strong, elongated bar. Our bar is much more compressed than this, and it has two main arms coming off of it, one off of each bar, and we can see that there's that the bar dust trail doesn't link up in the center. So the center here has its own wispy kind of orbit going around that's separate from the arms, and that happens in our own galaxy as well. When we're sort of looking at this bar formation, how does it form? We might start here with a flocculent galaxy. As things spin around, things begin to coalesce and elongate in the center, and we end up ultimately with some more pronounced arms, more well-defined arms with a bar in the center here. So we tend to think of barred spiral galaxies as being a little older and a little more mature, and flocculent galaxies as being a little younger and a little earlier in formation. Then we have elliptical galaxies. Here's a sort of typical elliptical galaxy with a lot of interesting darker gas and dust formations here. This is not dark matter. Dark matter is a different thing. We couldn't actually see the dark matter if it were here. So this is not dark matter, even though it's darker material. That's a different kind of thing. They don't tend to have a lot of stars forming in them. So we don't tend to have a lot of the H1, the hydrogen clouds that indicate stellar formation here. We don't have a lot of blue. Almost every elliptical galaxy we have is yellowish and reddish in color. So essentially they have three dimensions too. They're going to be tall, and they're going to be wide, and they're going to be long. They can be almost perfect spheres. They can be elongated into goose eggs and even a bit longer than that along the way. Almost all of them have large halos of low density but high temperature gases. And our Chandra X-ray observatory, which I've talked about a little bit here and there in our class, it's one of the NASA great observatories, actually can see the X-ray halos, the X-ray areas around these galaxies. We have a halo with hot gases as well around our galaxy, but these tend to indicate different kinds of things that have happened in the past, usually probably collisions. And it's thought, in the longest of long terms, our galaxy and Andromeda galaxy coming together will end up ultimately, after it goes through a period of losing the spiral arms and becoming a splatter irregular galaxy, will end up as a giant elliptical galaxy. And we'll probably have a lot of gas and dust in the X-ray halo that will indicate that along the way. Collisions are very important, as I mentioned before. And one of the things that we see is, just like our galaxy has those globular clusters, those clumps of stars that go every which way around the bulge and around the supermassive black hole as the center, ellipticals tend to have even more globular clusters than we do. So we've got around 150 more or less that we have identified along the way. If they have more around ellipticals, that's one more indication that these may have resulted from collisions taking place. Here is an elliptical one, again, with our sort of darker material, and we can see a little bit of an elongation here, although chances are good that's an artifact from the photograph and not from itself. And one of the reasons I'm saying that is, look at this star here too. That looks like it's some kind of optical thing. We've got a little bit happening down here in the corner as well along the way. So chances are, and that's one of the things we have to deal with when we're dealing with astronomy and images like this, we have to figure out what are we actually seeing and what's actually coming to us from the cameras and that don't exist out there. But one of the things we can see is we have this sort of fading away from the center. We do have this material that we could track and thus determine the kind of rotation that's taking place. We have some very small ellipticals and we have some supermassive ones. Some of the largest galaxies in the universe are in fact the ellipticals. And the black hole, the supermassive black hole picture that made the news recently, was actually the center of an elliptical, a supermassive elliptical galaxy along the way. And then here's a splatter galaxy, an irregular galaxy. Here we can sort of see clumps here and clumps here. We have a lot of blue here, we have a lot of red here. When things come together, when they smash together, they're actually not hitting each other physically. So we won't have two stars that hit each other. They'll go past each other, but the gas clouds and the material that are around them will begin to interact, and it will cause a burst of star formation. And that's why we have a lot of blue in newly collided irregular structures like we have this. So when we're looking at these, we look at younger collisions and we look at older collisions. When we're looking at the small and the large Magellanic clouds that are around our galaxy, they are both irregulars. In part, they're likely the product of smaller galaxy collisions, but they're also the product of our galaxy's gravity pulling them apart. So that makes a difference as well. They are much, much smaller than our galaxies by at least 2 orders of magnitude. And when we're looking at them from our perspective, again, we're looking at them from inside the Milky Way. In this photograph here, when we're looking at this, we can also see the small and the large Magellanic clouds. And that would tell us instantly, right away, this picture comes from the southern hemisphere, which in fact it does. Now, when we're looking at the different types of galaxies that are out there, as I mentioned before, we have our ellipticals, we have our spirals, which branch into 2 types. We have our regular spirals and we have our barred spirals. So those are 3 of the 4 types that I mentioned at the beginning. The 4th type is irregular and it doesn't fit anywhere on this tuning fork. But we classify them as E, as S, or SB. And E for elliptical can go from 0, which means it's almost perfectly spherical, all the way down to a 7 or so, in which it's going to be almost cigar-shaped. And then we have an S, an SO could actually be a barred spiral or not, because it's so tightly wound, it's sometimes hard to see anything that's happening inside of there. There aren't many of those, though. And then we sort of branch off, and the more unwound and the more arms it has, the sort of higher the letter, A, B, C. Then we put a B in here, and again, sort of the larger the structure we have, and the more unwound it is, we'll have the SBA, SBB, and SBC along the way. And we can even go beyond those classifications. There are some D and E classifications that are out there. Here's a picture These are elliptical galaxies, as we can sort of see. This is goose eggy along the way. This one here is also sort of almost flattened goose egg kind of thing. It's got some irregularities in it. It looks like gravity might be pulling in different ways around this. And this one here has a couple of other galaxies that may or may not be part of its entourage. We'd have to do analysis to see how far away those are relative to what we're seeing, because sometimes it can be here and then something way out here, or they can both be right next to each other. We have to do an analysis of the individual stars inside of them to figure it out. Here is a dwarf elliptical. It is nearby our Andromeda galaxy, so it's very small, only 2,400 light years across. So it's only about 1/10 of the distance of our solar system to our central bulge. So it's very, very, very small along the way, but it is seen in many pictures of the Andromeda galaxy. Here's a pinwheel. This is called the pinwheel galaxy, and it is seen face on. So sometimes we're seeing it edge on, sometimes we're seeing it face on, so we can actually watch it spiral here. Again, we see blue where the stars are forming as the rotation takes place inside of here. This is almost twice as big as our galaxy. So it's going to be huge, whereas we are about maybe 30,000 light years from our center. If this were ours, and we'd be maybe 100,000 light years across. This one's about 200,000 light years across. Our galaxy has 200 to 400 billion stars. This one contains 1 trillion stars, perhaps even more than that along the way. So the way we sort of figure these distances out, again, we're using the cosmic ladder, the sort of the distances. We've talked about parallax before. We can use that with relatively close things to see how they jump. Remember the experiment where you close one eye and put your thumb up and you watch things jump when you open the other eye. That method can be done for things inside the solar system, not so much for things outside the solar system, but it gets us to a certain point. Then we have a parallax with our spectroscopic information, which can be a little bit more subtle as we're watching things there. Then we use our Cepheid variables, and that can get us actually outside of our galaxy, and that can show us sort of the brightening and the dimming of key stars that we, again, use the word standard candles. And then we have a couple of different things that are a little trickier to define, like the Tully-Fisher law. As galaxies rotate and as they have varying luminosity, we can sort of figure out how far away they are based on that. And then if we're lucky, we can see supernova explosions, and we can actually, sometimes a supernova explosion will outshine the entire galaxy. And when we're lucky enough to see one of those, we can see those out to a huge, huge distance. And then beyond that, we use Hubble's law, which is how fast things are going away from us along the way. The parallax, again, that works here on Earth brilliantly, works in our solar system. We use something not too dissimilar. This talks about 10,000 parsecs, so we're talking about 30,000 to 35,000 light years away. So that's half of our galaxy, or maybe a third of our galaxy, really. We can look at things in our half of the galaxy, pretty much with this methodology, but not too much beyond that. Then we use our Cepheid variables. As I mentioned before, the brightness and the dimming will get us all the way out to some of the more distant stars in our local neighborhood, in our local group of other galaxies along the way. And the way we determine the distance is by looking at how bright or dim it is, because if we know whether it's a 40-day or 50-day or 60-day Cepheid variable, we know how bright it is intrinsically, because we've got some that are close up to us. So we will then be able to measure how far away it is by how dim it is relative to us. And we can sometimes see those here. Here's a Hubble telescope picture that we're getting from galaxy M100, 56 million light years away. Now this one that's behind me here, that's 2 to 2.5 million. So this is 25 times further out than that. And we're able to locate, notice we've got this thing right in the middle there that is dimmer, and then brightens and brightens, and we can sort of trace it over the course of time. and see how it brightens and dims, and that will tell us how far away this is. The Tully-Fisher law, as I mentioned before, we're looking at galactic rotation, and we're looking at the luminosity that's from it, so we can use that to help us determine how far away things are. And then we can use our supernova. Notice this very bright spot down here is almost as bright as the center of the galaxy. The center of the galaxy, the bulge, will have hundreds of millions of stars, and yet this one supernova outshines it. And we know how those operate because, again, we have them relatively close to us as well. Betelgeuse, 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 remember, that's the one that's most likely to explode in our lifetime, and it'll turn into something like this as well. Fortunately, we're far enough away that it's not going to do any damage to us, but it will be quite bright and spectacular when it happens. So any aliens in another galaxy will be able to use that supernova data to tell precisely how far away we are from them. Of course, it'll take millions of years for the light to get there in the first place. Here, again, we can sort of see the bright objects versus the entire galaxy that's taking place here. This is a standard candle or a standard bulb that we have. And then we have the radial velocity of galaxies. This is part of the Hubble issue. And Hubble isn't the only one who was responsible for this. Hubble gets the credit, but Besto Slipher was one of the persons who worked with Hubble and worked at the Lowell Observatory. If you remember, Lowell Observatory is famous for a couple of different things. Percival Lowell thought he saw the canals on Mars, and Clyde Tombaugh discovered Pluto from the Lowell Observatory. So this is an important place in the history of astronomy, but he worked there, and he shared his information there with Humason and Hubble. Humason was actually an interesting guy. He was sort of a self-taught astronomer. He helped build the Mount Wilson Observatory, and by helping build that, I mean he was actually a guy with the shovel and the dirt, and he was someone who would bring the mule teams up with the equipment up the side of the mountain, and at night sometimes it would be too late to go back down the mountain, so he would stay in the workers' shacks there, but they were already beginning to collect equipment and other things that would go into the observatory, and he just read and read and read, and eventually became one of the key assistants in the observatory itself, from just beginning by being essentially the mechanic and the mule train driver that's there. So he sort of reminds me, if you've seen the movie Good Will Hunting, where the guy's the janitor, but he's also solving all of the math problems that none of the other math kids can figure out on the board. That's what Humason was. And Humason and Hubble looked at the different information that was coming off of the photographic plates. And what they often would do is they would have these glass plates that they photographed things on, and they would switch them out and do different types of analyses. That was how Clyde Tombaugh found Pluto, by the way. He'd look at one plate and then another plate and another plate and another plate, and sort of look for where the differences were to see what was happening between the two. And one of the things that they discovered was that the further away something is, the more the red shift occurred on the different elements that we were getting off of the spectrographic information along the way. So we have Hubble's data, then we have sort of updated with Humason's data. So what we're sort of figuring out is not just that our things are going away from us, but that space itself is stretching along the way. So while we might have all these ants walking along the ruler here, as they're walking along, the ruler is also stretching out along the way. So think about walking on a treadmill, but you're also walking on a treadmill as the treadmill gets longer and longer and longer. So we not only have the galaxies themselves moving, but we have the space between the galaxies also expanding. So we get what's called a cosmological redshift. And I know I've used this image before of, say, the raisin bread in the oven expanding. Let's say you're on this central raisin right here where all the lines are coming off. And as you're sitting on that raisin, as the loaf expands in the heat of the oven, all of the raisins seem to be going away from you. The further ones seem to be going away from you faster because more of the bread is expanding away. The closer ones don't seem to be going as fast because they're already closer. There's not as much bread to expand between it. That's what's happening in the universe. So things that are further away already are going away from us faster because there's more space between them. And that's true for pretty much everything outside of our local group. That does not apply to Andromeda here. Andromeda is close enough to us that the gravity of Andromeda and the gravity of the Milky Way are pulling each of them together along the way. But once you've gone far enough away that the pull of gravity has diminished to being almost negligible, the expansion of space takes off, and that's what's happening. We have a redshift. And then, of course, as I mentioned before, we have new science. Welcome home to the black hole images. This happened just last year, almost exactly 1 year ago. And what happens in a black hole, we've talked a little bit about this before. In any object, any massive object, well, really any object, will curve space-time around it, but the more massive it is, the greater the curvature. A black hole draws the light into it so far that it cannot escape once it goes beyond the event horizon. We were able to put together quite a number of observatories. These are our radio observatories that are around the world, and to lock on to a couple of different black holes, one of which is our supermassive black hole at the center of our galaxy, but the other is at the center of that giant elliptical galaxy that I was talking to you about before. And as we're looking at this is called the Event Horizon Telescope, this whole big collection of telescopes that are working together. These are called collectively the Event Horizon Telescope because they would all look at the at the object, and they would then feed all of their data back to a central collecting point that would then assemble the data. And you can see we have things in Hawaii, we have things down in the Atacama Desert in Chile, we have one in Mexico, we have our arrays out in the American Southwest, we have one up here in Greenland, we have one down here in Antarctica. So when we're using these, we're almost simulating having a dish almost the whole size of our planet as we're looking at it. We have more that are coming online, so we'll get even better resolutions as things go along. If you're looking at something with a single dish, you'll get some pretty good measurement. If you use standard interferometry, which is sort of chaining things together and looking at it at the same time and simulating having a larger dish, you get a better image. But the techniques that were developed for the Event Horizon Telescope outshine that by a large degree, 40 to 50% better. And you can sort of see how our resolution gets better and better. And by the time we're putting in ALMA with this, it doesn't expand our baseline, but it collects more material and we can see it in greater detail. And this is what we get. And this is actually so much data, it would literally break the internet. This is a Kardashian event here. So this would break the internet. In fact, it had so much data that was collected, it couldn't be sent via the internet. What they had to do is they had to get these massive, massive hard drives and then physically bring them together and chain them together so that we could draw off the data from each of them. But this is a typical image from the Chandra X-ray. Again, our Chandra Great Observatory up in space above our atmosphere, taking close-ups of the midpoint of the galaxy that's here. And then as we look, what we're seeing is we're seeing the disk of material and the energy around the black hole. We can't see the black hole itself, but we can see over the course of several days shifts and movement taking place. And we're not looking at it directly on the side, and we're not looking at it directly face on. We've got it at a weird angle there, which is why we've got sort of brightening and dimming along the way as we're seeing things here. Here are all of those different kinds of hard drives that had to be assembled together. 5 petabytes, 5 billion gigabytes of of material that had to go into this. So you think about my computer. I have 1,000 gigabytes on my hard drive that's here. That means I'd have to have 5,243 of my computer chained together to get this kind of image. Katie Bowman here, look at the smile on her face, but also notice she's not that much older than the typical grad student that's there. So don't ever let gender, don't ever let age, don't ever let race, don't ever let anything stand in your way if you've got a great idea, because that's what this came from. This came from her ideas. And if you've got an idea, float it out there and see what happens. I love this image too, because when people were working on the Apollo missions, there was so much paperwork and there was so much data transcripting and so many data tapes and other kinds of things. It's almost impossible to imagine. But here we have Margaret Hamilton, who is one of our key thinkers and engineers in terms of getting our Apollo missions to the moon. Remember, back then they didn't have computers and stuff like we have today. And today we're doing similar kinds of data things, although all of this stack would fit in about maybe 1/1000th of this collection of data here. So we're getting better and better and better along the way. So I thank you for joining me on this. I hope that you enjoy looking at galaxies, and I look forward to chatting with you again.